Good evening all. In the last class, we were discussing about string efficiency. This is applicable with suspension type insulators. So we have to derive the expression for string efficiency. These topics we have seen in the last class. So when voltage is applied across the suspension insulator string, it is unequally distributed across the individual unit. The disc near the line conductor is extremely stressed. The voltage distribution on insulator string determines the flashover voltage and the voltage at which the localized corona and radio interference is produced. Here you can see the installation of the suspension insulator having 3 discs. And one end of the disc is connected with the cross arm and the other end is connected with the conductor. Now, the disc nearest to the conductor will be stressed most. This will be lesser stressed, and the disc near to the cross arm will be least electrically stressed. The insulator material between two metallic pins form a capacitor of capacitance C called self-capacitance. Also, the air between each pin and the tower form the other set of capacitors. These capacitances are called capacitances to earth. So, this is the capacitance to earth and this is the self-capacitance. C is known as self-capacitance and C1 is called capacitance to earth or mutual capacitance. Here we can see the voltage distribution. V1 across the disc near to the cross arm, then V2, V3 is the voltage across the disc nearest to the conductor. Total voltage across the conductor and the earth tower is V. So we have to define the various parameters as per the diagram. C is the self-capacitance of each disc. C1 is the shunt capacitance between metal link of string insulator and tower. V1 voltage across the first disc near to the cross arm. V2 voltage across the second disc. V3 voltage across the third disc, that is nearest to the line conductor. Then V is the voltage between conductor and the tower. Let C1 by C, that is mutual capacitance to self-capacitance, be a factor called K, so that C1 is equal to K times C. Now applying KCL to node P, that is the point here. Here you can see the marking of currents. I1, capital I1 goes upward. I2 is the incoming current. Small I1 is the current leaving towards the tower. Okay. So with this, applying KCL to node P, we get incoming current I2 is equal to outgoing currents I1 plus small I1. Now, this currents can be replaced with voltage multiplied by voltage divided by capacitive reactance. So, capacitive reactance is 1 by 2 pi Fc. So, current is equal to V by capacitive reactance, that is equal to V2 into omega C. That is equal to V1 omega C plus V1 omega C1. So, corresponding to these currents. The currents are flowing through these capacitive reactances. Hence, V2 omega C is equal to V1 omega C plus V1 omega C1. Or V2 omega C is equal to V1 omega C, and we are substituting for C1 as Kc. So, we are getting V1 omega Kc. Now, V2 is equal to V1 into 1 plus K. Omega C will be cancelled on either side. So, let this be our first expression. Now, consider node Q. If we consider node Q, we can see I3 is an incoming current, capital I2 is outgoing current, and small I2 is also outgoing current. Capital I2 flows through C, I3 is also flowing through C, small I2 is flowing through C1. So, applying KCL to node Q, we get I3 equal to I2 plus small I2. Or, in terms of voltage divided by capacitive reactance, this will be V3 omega C equal to V2 omega C1 plus V1 plus V2 omega C1. This is equal to V3 omega C1 is equal to V2 omega C plus V1 plus V2 omega Kc. We are substituting for C1 in terms of Kc. V3 equal to V2 plus V1 plus V2 into K, or it is equal to KV1 plus V2 into 1 plus K, or KV1 plus V1 into 1 plus K the whole square, or V2 is equal to V1, we have V2 is equal to, from equation 1, V2 is equal to V1 into 1 plus K, or V3, we are substituting all this for V3, V3 is equal to V1 into 1 plus 3K plus K square. Let this be our second expression. Now again, one more node is there, that is R. So between conductor and the earth, here we shall consider the voltage between conductor and the cross-arm or the tower. It is equal to capital V. Capital V can be written as V1 plus V2 plus V3. We can substitute from equations 1 and 2 for V1 and V2. So we are V1, V2 and V3. So V1 we will keep it as such. V2 is equal to V1 into 1 plus K. V3 equal to V1 into 1 plus 3K plus K square. So on reducing and rearranging, we will get V as V1 into 1 plus K plus 3 plus K. From equation, let this be third expression. From equations 1, 3 and 1, 2 and 3, we get V1 by 1 is equal to V2 by 1 plus K is equal to V3 by 1 plus 3K plus K square is equal to V by 1 plus K into 3 plus K. Or V1 is equal to V by 1 plus K into 3 plus K. Now V2 is equal to V1 into 1 plus K. V3 is equal to V1 into 1 plus 3K plus K square. Now percentage string efficiency is defined as voltage across the string, total voltage across the string, divided by N into voltage across the unit nearest to the conductor. N is called number of discs. If we are having a 3-disc system, the expression becomes the total voltage across the string. We have defined it as capital V. Then number of discs 3. So substitute 3 for N. Voltage across the unit nearest to the conductor V3. So it will be equal to V by 3 into V3 into 100%. String efficiency is an important consideration since it decides the potential distribution along the string. Greater the string efficiency, the more uniform is the voltage distribution. This 100% string efficiency is an ideal case for which the voltage across each disc will be exactly the same. Although it is impossible to achieve 100% string efficiency, yet efforts should be made to improve it as close to this value as possible. If the unit of the line conductor is about to flash over, then the whole string is about to flash over. In this condition, the string efficiency is expressed as flashover voltage of string divided by N into flashover voltage of 1 unit. So, it is better to have greater string efficiency. So, there are certain methods to improve string efficiency. We shall see those methods in the next class. Thank you.